Last class we were discussing regarding ASK and FSK. Today's discussion will be all about PSK. Okay, so today we will going to discuss regarding phase shift keying. Okay, so ASK means you are aware, amplitude shift keying. FSK means frequency shift keying, and today's discussion will be all about phase shift keying. Okay, now in this phase shift keying PSK, the signal element used is phase. Okay, the phase is the signal element which will be used to transmit the data or to represent the data. How exactly it will be done? Okay, so we'll see it by say taking some waveform. Okay, so as usual we need a support of a carrier here. So this carrier signal, basically the phase of this carrier will going to be changed, but whereas amplitude and the frequency of this signal will going to be kept constant. It is not changed. Okay, so I'll talk regarding a signal with two different phases. Okay, now here you see the carrier uses one phase to represent say 1, but when it comes to a representation of other bit, okay, so rather than talking regarding say taking this particular value, I'll just try to change it this way so that you can understand how exactly the phase will going to be changed. I slightly shortened it. You see, this is my 1, but when it comes to a representation of 0, you see the starting say portion of this waveform, it starts from 0. So that means the phase of this is 0, whereas I am talking regarding another signal with a different phase. Yes, so this is my 0. Now see, this change in the phase is used to represent the data. So here in phase it is 180 degrees out of phase. Now see, this is 180 degrees out of phase signal whose phase is which is representing data element 0. Okay, so again when it comes to representation of 1, I'll use the same strategy. Okay, change in the phase. In phase signal will be used to represent say your 0. Sorry, 1 will be represented by in phase signal and 0 will be represented by out of phase signal. So this is 0 and 180 degree, two different phases we use over here for representation of the data element. Okay, so 0 is representing one data element, 180 degree phase is representing another data element. So this is what is the criteria that is used in PSK. That is the reason we call it as phase shift keying. Okay, now when you look at the way in which this phase shift key will going to be generated, what is the say technique that we need to use to generate this phase shift keying? It is nothing different from that of ASK. Just recall that what we discussed in a ASK, okay, how we generated a ASK. So the simple technique that what we used for the generation of a ASK is I used one multiplier. So we used one multiplier. One input of this multiplier is your data stream. So this data stream is required to be represented in the form of a digital signal. Then the other input is from oscillator. Okay, it is from the oscillator which is generating the carrier signal. Okay, so this is the carrier signal which is going to be generated by this oscillator. Fine. Now you are talking of using some kind of a multiplier, okay, which will going to generate this output. Now when you look at the arrangement, okay, so when you look at this arrangement, it remains same as that of, say, your ASK, amplitude shift key. So I told you that the biggest advantage of ASK generation is its simplicity. Okay, so now when I talk about the PSK, it is also as simple as that of ASK. Okay, so the main reason here is the signal element is, say, with phase and 180 degrees can be seen as the component of the signal element with phase 0. Okay, say now basically here we are talking regarding two phases, 0 and 180 degree. This, say, gives us an idea how exactly to implement this BPSK. Okay, so we used that, what idea we used in this ASK, same idea will be used. Okay, but only thing is, in an ASK we generated it using a, say, polar NRZ signal, whereas here we will go to use, say, here we will go to use polar NRZ, whereas in case of ASK we used unipolar NRZ. Okay, only change is this, only change in representation of this digital signal. Okay, we talk of using a polar NRZ here. So this polar NRZ will help me to generate that different phases. So this is only the difference. So in case of your ASK, the signal used, say this bit stream, everything remains same. Only way in which the signals are generated, digital signals are generated, that makes the difference. So in case of ASK, we used this kind of representation, unipolar NRZ, whereas in PSK we used, say, polar NRZ scheme, so which generates the signal with two different phases. So mainly because of these two voltage levels, minus and, say, plus. Okay, I hope it is clear to you. So this is how the PSK will going to be generated, and this is having an advantage same as that of your FSK, same as that of your FSK. What all the advantages you get in a FSK or ASK? Okay, I am just talking the relative advantages. Okay, so the basic relative advantage what we get in a FSK or PSK, ASK, is that frequency is the component, frequency is the signal element which is used to represent the data here. So this helps us to suppress the noise. Okay, normally I said you in the last class that amplitude will be most affected by the noise. Now ASK eliminates the problem of, say, noise effect in the signal. Now similar advantage or same advantage you will going to get in a PSK. PSK too have, say, no effect of noise on it, because the signal element here is phase. Now noise will not going to affect the phase of the signal. Noise will not going to affect the phase of the signal, but change in the amplitude will not going to make any difference for the PSK. Basically the signal element is, okay, so phase will not going to change, amplitude will going to be changed. So naturally, what is again, when I compare PSK with the FSK, what will be the advantage? The advantage is bandwidth. Whatever the bandwidth that ASK uses, okay, whatever the bandwidth that ASK, just I will write the bandwidths of both FSK and ASK. The bandwidth of ASK is this. Okay, this is bandwidth of ASK. Yes, the bandwidth of FSK, just recall that 1 plus D into S plus 2 delta F. I need to add one more additional component, that is 2 delta F. It will increase the frequency, it will increase the bandwidth. It will increase the bandwidth, that additional thing. Now when I talk about the PSK bandwidth, it is same as this. It is same as this. So PSK bandwidth is, okay, it is equal to 1 plus D into S. Okay, so that means it has a bandwidth same as that of ASK. So that means it is taking the advantage of ASK. It is, say, not getting affected by the noise. So that means FSK's advantage is also part of it. So compared to these two things, it is, everything is a gain. Everything is a gain. It has all the advantages of FSK. It has all the advantages of ASK. Okay, so naturally it is totally, say, better scheme compared to other two. So that is the reason in most of the mobile communications and mobile communication applications and all, we prefer to use, say, PSK or other schemes. Okay, so you will come to know how exactly it will be an advantages. Now I hope it is clear to you. So the implementation part and all. Okay, so now I will talk regarding the issue. Now in all these discussions, in these three discussions, I was concentrating only on what? Representation of 1 bit per signal element. One signal element is equal to one data element. This was the concept I used, or this was the, say, basis I used for generation of the signal. One signal element, one data element. So that is the reason when it comes to R, I said it was 1 in all cases. In all cases, I was talking regarding the R value is equal to 1. Okay, R value is equal to 1. Now we'll talk of, say, the newer methods, which will see, these are all basic things, basic concepts. So when it comes to actual communication systems, we will not rely on these basic things. Okay, basically one signal element equal to one data element, that will not be a bigger advantage. It will not help us to increase the, say, data rate and all. You see, you people are talking regarding 3G, 4G, 5G. Okay, say one of the methodology that is adopted in these schemes, okay, in these different standards, is, say, this representation. How many number of signal elements will be used to represent how many number of data elements. So normally what we prefer is one signal element. We expect one signal element to represent a more data element. We expect one signal element to represent a more data elements. Okay, so that means if you, say, have a more number of bits to be represented by every signal element, then we call it as advantageous schemes. Basically it helps us to increase the data rate. We have already discussed or talked regarding this in the Nyquist criteria. Just recall that, say, Nyquist theorem, in which we told regarding the same. Okay, as number of levels of the signal increases, it increases the data rate. Okay, as number of levels of the signal gets increases, it increases the data rate. Okay, so that means our interest is number of levels in the signal indicates you are talking of, say, representing more data element per signal element. Okay, now I will talk regarding, first I will talk regarding, say, PSK, then I will come to a ASK. Okay, so what exactly the PSK, how exactly I can increase, say, number of data elements per signal element. So the idea is simple. So in the previous case, I used a signal with two phases, 0 and 180 degrees. 0 and 180 degrees. So now I will talk about some particular scheme. Okay, now I will talk regarding some particular scheme in which I am going to use 4 different phases, that is 45, minus 45, 135 and minus 135. So these are my 4 different phases. These are my 4 different phases. Okay, I am talking regarding 4 different phases. So which will now going to be helping me to increase number of bits per signal elements. Number of bits per signal element. Now see, when I have a 4 levels of signal, See, actually in PSK, okay, in multi-level PSK, you can call it as a multi-level PSK, where if I have an option of generating, say, signal with more number of phases, okay, so this will help me to represent a more number of bits per signal element. Now see how many phases are there? 4 phases. Okay, how many bits I can represent? Say 4 phases are my signal element. Phase is a signal element in a PSK. So every phase now will be used to represent a 2 bits. Every phase will now going to be used to represent a 2 bits. 0 0 0 1 1 0 1 1. Yes. So this is what is an advantage, or this is what is how I can increase the data rate. Clear? So this one signal element, more number of bits. Naturally, in the lesser bandwidth, I can increase the more bits. So this helps me to increase the data rate, which will give us an advantage when it comes to a data transfer operations. Okay. So these type of techniques itself they use in 5G and all. Okay, especially in 4G schemes and all. Okay, so these type of say schemes where they try to represent more data bits per signal element. Okay, so that gives them an advantage of generating the required data rate. Okay, so that is why we say that 5G is faster compared to that of the 4G and all. Okay, so one of the criteria that is used in these higher standards is to increase number of bits per signal element. One of the criteria. It is not the alone one which increases the data rate. So this is one of the criteria that is helping to improve the speed of the data. Say if one signal element carries more bits, naturally it will have an effect on say data rate. Okay, so speed of transmission will also increase. So first we'll talk regarding one such scheme which is connected with PSK. We're going to call it as Qpsk. Qpsk. So what exactly a Q means? Qpsk means Q here indicates quadrature PSK. Okay, Q indicates it is quadrature PSK. Phase shift keying. Quadrature phase shift keying. So Q indicates quadrature, say PSK is phase shift keying. So this we will going to talk regarding. We'll see how exactly Qpsk will be say generating 4 different phase signals and how it will help us to improve, or how exactly it will help us to represent 2 bits per signal element. Okay. Now the arrangement for generation of such a signal is simple again. I don't need too much of complicated circuit here. As you know that we are using multiplier. We are using a multiplier for generation of PSK. Same arrangement. Say I am not going to use something new. So 2 multipliers. Previously I was using only one because my say requirement is to represent 1 bit per signal element. So my requirement is changed now slightly. So for that reason, way in which the circuit or way in which the arrangements that are needed for generation of such signal is slightly different. Okay, but overall basic idea remains same. Okay, so I'm going to have some kind of a say oscillator. I'll draw it over here. It is better. So it is my oscillator. OSC indicates oscillator. Okay, so this oscillator will go to generate the required frequency signal, which is carrier signal. Now look at this. The signal which is going to be fed to this multiplier is 90 degrees out of phase compared to this. Okay, so here I am feeding a signal which is in phase. Okay, so in phase signal, whereas this multiplier is getting a carrier signal which is 90 degrees out of phase. So when I talk about the phases of these 2 signals, say it is in phase signal, it is 90 degrees out of phase signal. Okay, so this is in connection with carrier. Now this is what is the requirement. So we need to apply the input to it. Okay, so we need to make some slight change when it comes to application of the input. what I need is, I need some arrangement. Okay, I need some arrangement which performs, say, serial to parallel conversion, the input bits which are coming over here, which are, say, serial in nature, that is required to be converted to a parallel. Okay, so that means I am not talking of generating say signal with 8 bits in fashion. Here serial to parallel conversion means a simple arrangement. 2 bits will going to be clubbed. 2 bits will go to, say, the parallel line is capable to hold 2 bits at a time. Okay, it is capable to hold 2 bits at a time. Is it clear? So this is what is an arrangement I am going to use. So this is my, say, 2 by 1 converter. Okay, so this converter helps me to convert serial to parallel. Okay, so these serial to parallel converted signals will now going to be fed to these multipliers. Now these will going to make a second input to these multipliers. There are 2 inputs now. This is one from oscillator, one from this, say, converter. Okay, so why we need this converter is basically, see, whenever we start an operation, whatever the signal it is generating, same time we need to apply both the inputs to these multipliers. 2 bits are required to be applied at same time. 2 bits are required to be applied at the same time to this multiplier. This is what is an idea. So for that reason, we are talking of converting this serial to parallel. So these bits gets converted to a parallel. So these parallel bits will be now fed to these multipliers. Okay. Now see what exactly the changes that will happen in terms of time. Say if time duration of every bit on this input line, if it is 2t, now you have converted 2 bits, you are generating 2 bits at this point, at this part you are generating 2 bits at a same time. That means it has to wait for a 2t times, because each bit has a duration of t seconds, so it has to wait for 2t seconds. So that means duration of the, say, bit on these lines will go to be 2t. It is 2t. Say duration of each bit on these lines will be 2t. Please keep this in the mind. Okay, duration of these bits will be 2t. Here it is t, whereas here it is 2t. Okay, so this arrangement helps us to generate the thing. Yes, so now here it will going to generate a data, and that Psk will be used to represent the data over here too. So whatever the bits that are coming here, that will going to be represented by the 2 signals of 2 different phases. Say as it is, these signals are 90 degrees out of phase. Say for example, say if I talk of using a signal with 45 degrees and 135 degrees over here, so naturally here it will be minus 45 degrees. See, 90 degrees out of phase. And when I talk about, say, 90 degrees out of phase with respect to it is 100. So as it is here, it is 90 degrees out of phase. So whatever the signal it gets generated, for that you add one, say, to make it 90 degrees out of phase, it is 135. So this way it generates a 4 signals which are in turn gets, say, summed at this point. So I will going to use something known as a summer here. This here it is multiplier, here it is summer, which sums these 2 signals and generates the final composite signal which contains the 4 phases. Okay, the final signal which will going to contain the 4 phases, So this is what is the arrangement that is we used for a generation of quadrature Psk. Okay, this is what is an arrangement that what we used for a generation of quadrature Psk. So I will just show you how exactly this quadrature Psk, that one particular signal will going to be generated. It is difficult to digest because that, say, phases involved are slightly, say, it makes a bit difficult for representation, but anyway I will try to show it to you over here by taking a 4 different phases, how exactly your output will going to look like. Okay, so your carrier and your bit stream I am not going to change. Okay, so at the beginning I have to say start with 2 bits at a time. Okay, 2 bits at a time. So first I am going to start with a signal with minus 135 degrees. I'll assume that minus 135, you see this particular phase, which is meant for representation of 2 bits. Yes, 2 bits. So this phase will go to represent, I'll assume that it will go to represent 0 0. It will represent a 0 0. Next phase I'll use, see, it is in some particular sequence I am using so that you can understand it better. So for that reason, so next phase which I am going to use for representation is, see, I am talking about complete 3 cycles. It starts from here, it ends over here. Okay, so the next is, I'll start with minus 45 degree signal. I'll talk about, say, see, look at this phase. That is the reason I said it will be a bit complicated for me to represent it. Yes, so just try to understand there is a change in the phase. There is a change in the phase. So this will going to make me, give me a signal of, say, size minus 145 degrees. Okay, now I land it over here. So this is my minus 45 degrees. Okay, this is minus 135 degree phase. This is minus 45 degree phase. Okay, you see these two are starting from a negative side. So it is first is minus 135. Next one is minus 45. You see this is, look at this portion of the signal. So more than half has been pushed inside, whereas say it's starting, it's before the peak itself, its phase has been started. So that means there is a change in the phase. So that is what is representing the phase. Okay, next is minus, I will talk regarding the plus 45, plus 135. Yes, this is the phase which is plus 135. Okay, this is the phase which is plus 135. Okay, last one, again it has to be a up from positive side, from positive side. So as you know that it has to be this way. Yes, so you look at this phase, it is going to represent plus 45 degrees. So minus 135, minus 45, plus 35, plus 45. Like this I have a 4 different phases. So which will go to now represent a your 0 0. This will represent a 0 1. So that's the reason I said I am generating it in some particular sequence. It will go to represent a 1 0, 0 1 and 1 1. So plus sorry, it has to be 1 0, 0 1, minus 135 0 0, minus 45 1 0, plus 135 0 1, and plus 45 is 1 1. So like this, two signal elements are represented by, two data elements represented by one signal element. Signal element is phase. Minus 1, I'll write it over here for understanding reason. So minus 135 is one signal element which is representing 0 0. Minus 45 is another signal element which is representing 1 0. Plus 45 is another signal element which is representing 0 1. Whereas plus 135 is another signal element which is representing, sorry, it should be 0 1 and it should be 1 1. Okay, so like this I have 4 different signal elements which are representing 2 bits. So that means your R will go to be a battery in this case. Okay, so which is in turn helping us to improve the data rate. In turn helps us to improve the data rate. I hope it is clear. So this is regarding quadrature. PSK. Okay. So is this the method that what we use in mobile communications and all? No. We are looking for another better approach which helps me to represent more number of bits per signal element. Okay. So that is your QAM scheme. QAM. Okay. Quadrature amplitude modulation scheme, where we are clubbing a PSK and ASK. Look at this. So now I am talking of clubbing multiple, say, modulation schemes to improve the data rate. So we clubbed PSK and ASK to generate or to improve the data rate. So this is one of the techniques that I am going to discuss it in the later part, not today. I am going to discuss it tomorrow in tomorrow's class. Okay. So what exactly, how exactly to combine this PSK and ASK. Okay. So before concluding this today's discussion, now I only talked regarding PSK, how exactly PSK is helping me to improve the, say, data rate. Will it not be possible with a FSK or a ASK? Yes, it is also possible with ASK and FSK. You see, in FSK, the signal element is frequency. It is signal element. Frequency is signal element. Okay. Now somehow I should generate more number of signal elements which helps me to improve number of bits that are represented by each signal element, which will help me to improve the number of bits to be represented by each signal element. So the thing that what we have discussed in FSK, which was, say, using only two frequency components. Okay, two frequency components, one is with high frequency, another with low frequency. So this is my F2, this will be my F1. Like this, I used two frequency components to generate FSK. This is what we have discussed in last class. So now what I am suggesting is you go for a signal with four frequency components. Four frequency components: F1, F2, F3, F4. Okay. So now frequency is the signal element. So I can improve the data rate by representing more number of bits per signal element. Since there are only four signal elements, so I can represent 2 bits per signal element, because number, see, this indicates number of levels in the signal: 1, 2, 3, 4, 4 levels. It allows me to represent 2 bits per level. Okay. Now when I talk about ASK, okay, when I talk regarding ASK, so ASK, okay, in ASK the signal element is amplitude. So how can I improve? The improvement is possible by taking a different amplitudes. So in the previous discussion, I used two amplitude signal. One was 0 and another was, say, plus V. So these are the two amplitude values I have selected, say, for representation of 1 bit. 1 bit with every signal element. I'll just redraw that figure, you see. So this was an arrangement that we used to represent 0 and 1. This is used for representation of 1. This was used for representation of 0. Now what I am saying is increase number of amplitude levels. So that automatically increases the number of signal element. In turn, it improves, say, helps me to add more number of levels to the signal element. Yes. So just one way of increasing it is this: I'll start with one amplitude signal, then I'll change its amplitude to a different level, then third amplitude level signal, and fourth one. Like this, I have a 4 amplitude level signal. So the amplitude is the signal element. Number of levels in the amplitudes are 4. So which helps me to represent 4 bits. I'll start with 1 1, 1 0, yes, 1 0 0 1, 0 0. So like this, I can represent a more number of bits per amplitude. But as you know that ASK, there is a lot of possibility that noise will go into affect these amplitudes. So this is what is a problem with multi-level ASK. These schemes we call it as, say we will add a term multi-level in front of it. So when we talk of using a more number of frequencies, we call it as multi-level FSK. More amplitudes to represent the data bits, that we call it as multi-level ASK. Okay, so these things helps us to improve the data rate. Okay, so basic idea is just by increasing more number of signal elements. So this is what is an idea we have used over here. Okay, next is as I said, that quadrature amplitude modulation scheme, Qpsk. Okay, that I am going to discuss it in the next class, so that we can attempt some examples on the same. Now, before concluding this, okay, I'll discuss one example which is related to Qpsk, say quadrature PSK, how exactly it will help me to improve the data rate, that we will see with this example. So I'll first read out the problem statement of this Qpsk. Okay, I'll write it over here. Say that is, find the bandwidth for a signal. Find the bandwidth for signal. Find the bandwidth for the signal transmitting at says I am using certain notations like at for signal, this is the notation, bandwidth, this is what is the notation. Okay, because of the space reason and all. Okay, say transmitting at 12 Mbps. Okay, 12 Mbps for Qpsk. Okay, so these are the data that they have given. This is what is the data they have given in connection with Qpsk. And one more value, that d value it is given, d is assume d is equal to 0. This is what is the assumption they have mentioned. Okay, they are asking us to find the bandwidth for signal transmitting at a rate at 12 Mbps for a Qpsk. You know that, say in Qpsk, 2 bits are carried out. How many bits you are transmitting per signal element? 2 bits. Yes, 2 bits are getting transmitted or carried by every signal element. Okay, so this means that, say I am talking regarding R. Now see, R value is 2 because 2 bits per signal element. Fine, 2 bits per signal element. So that ratio will go to be nothing but number of data elements divided by number of signal element, that is R, is equal to 2. So R value is 2. So R is a ratio n by s, where n is number of data element, where s is number of signal element. Okay, so the signal rate now we need to find out. So in this case, signal rate is given by this formula, S is equal to just n into 1 upon R. Now see, we have already proved that S is proportional to bandwidth. If I calculate what is S, I can safely say that S is equal to bandwidth. So later on I will equate those two and I will say that this is what is the bandwidth